Good morning. Welcome to this day about analysis of variance, ANOVA, and I put together content like this. 5 different headings here. So we start off with ANOVA for independent measures. That means we have only one value each for each individual on the dependent variable. So it's not repeated measures. That's what the word independent there refers to. And the word independent and dependent, they can mean a lot of things. For instance, that we don't have repeated measures, that's independent. We also talk about dependent and independent variables. Have you come across those? Dependent variable, if we're going to look if something has an effect on something else. If X has an effect on Y, then Y is the dependent variable, and X is the independent variable. So we are analyzing if one or more independent variables have an effect on, well, in our case, one dependent variable. Well, one way ANOVA, it stands for then we have only one independent variable. So we have one independent and one dependent. Two-way ANOVA, then we have 2 independent variables and 1 dependent. So always one dependent variable. And that's true for all analysis we're going through. So if you're going to have a look if some kind of medication has an effect on health, then you have a look, then medication is the independent variable and health is the dependent variable. In ANOVA, the independent variables are always categorical. They are not continuous. So people belong to one of a few groups. If you have continuous independent variables, then you don't do ANOVA. Then you might do regression analysis instead. So we have one way, one independent variable, 2 independent variables, and then we have a look at 3 independent variables. Of course, you can have even more than that. But here we go to ANOVA for dependent measures, which is the same as ANOVA for repeated measures. So we measure our individuals' values on the dependent variable on several occasions. 2 or more occasions. So repeated measures. And then we top off with a mixed ANOVA here. Then we have both repeated measures. So we measure our persons, our individuals, on the dependent variable on several occasions. But the individuals also belong to different groups. So here we can have a look at, does the value on the dependent variable change over time? And is that change affected by what group you belong to? So you get a time group interaction. And you can have several between subject factors. So individuals can belong to one of several combinations of independent variables. And the most complex analysis we're going to have a look at here is when we have 2 between subject variables and repeated measures. So that's the last mixed ANOVA we're going to have a look at. So we start off easily here, softly, with a one-way ANOVA. You see, it's clear-cut. You just follow the road here. So we have measures of 2 or more samples on a continuous variable. So people belong to one of several groups, 2 or more groups. And they have a value on a continuous variable. Because what we're going to do here is that we compare means between the samples. Is there any difference in the mean between the samples. And then, of course, we will have to be able to calculate the mean. And you can't calculate the mean, for instance, on a variable on a nominal scale. So you can't compare if there's difference between average country of birth between various groups, because you can't calculate the mean on a variable as country of birth. So we have a continuous dependent variable. And we do this in the form of hypothesis testing. So we compare two hypotheses, call them null hypotheses and alternative hypotheses. A null hypothesis says that all the populations that the various samples represent have the same mean on this dependent variable. The mean is the same in all populations. And the alternative hypothesis states the opposite. Not all populations have the same mean. At least two of the populations have means that differ. Okay, we calculate the probability of getting the data we have, given that the null hypothesis is correct. If the populations really have the same mean on this dependent variable, what is the probability of getting samples where the means differ from each other as much as it does in our data? That's what we calculate. That's our p-value. We have a look at this p-value and we draw a conclusion. If it's lower than our significance level, lower than 0.05, we reject the null hypothesis. We say that if the null hypothesis would have been correct, the probability of getting the data we have is so low that we assume that the null hypothesis is wrong. We assume that there is a difference in the mean on this dependent variable between at least two of the populations. If the p-value, the probability, is higher than our significance level, then we say we can't with enough confidence reject the null hypothesis. Therefore, we keep it so far. So it's the same rationale as between t-test. So let's imagine we have 3 samples drawn from 3 different populations. And it looks like this. So we have 3 different cases. Can look like that. So we have variation. We have variance in the samples, but we also have differences between the sample means. So 3 different cases. So which of these 3 outcomes is most probable if the null hypothesis is correct? If the 3 populations have the same mean on the dependent variable, which of these 3 outcomes is the most probable? The first one. So here we have the highest p-value. This outcome is most probable if a null hypothesis is correct. Why is the p-value lower in this second case compared with the first case? Why? Why is this outcome less probable than that one, given that the null hypothesis is correct? Exactly. There is a larger variance between the groups here. Larger difference between the group means. So the bigger difference we have between our sample means, the lower the p-value. The lower is the probability of getting that data if the null hypothesis is correct. But here you see in the third case and the first case, the difference between the sample means is exactly the same. But why is the p-value lower in this third case? Why is the probability of getting this data, given that the null hypothesis is correct, lower compared with the first case? Why? Less variance within samples here. So what affects the probability of getting our data, given that the null hypothesis is correct, is differences between the sample means and variance within the samples. The bigger the difference between the sample means in comparison to the variance within the samples, the lower is the p-value. And then, of course, we also take into consideration the sample sizes. So variance between groups and variance within groups. That's what we're going to analyze with ANOVA. So if we take samples from a certain population and calculate how much the sample means vary, how much they differ from each other on average, we see a relation like this. The larger the samples, the less they tend to differ from each other. And we have a formula here. It says the standard error equals standard deviation divided by the square root of the sample size. So what is this? This standard error. Well, it's deviation between sample means. The more the sample means deviate from each other, the larger the standard error. And the standard deviation here is the same thing, but on individual level. The average deviation between individual values. And this formula is correct when you draw individuals or samples from the same population. Then you have this relation. Or if you draw individuals and samples from different populations that have the same mean, then you have this relation between variations between samples and variation between individual values. So this is true given that the null hypothesis is correct. So let's do something with this formula. So we have a formula here. Standard error is standard deviation divided by the square root of the sample size. We square all the terms here. What does this say? Well, it says variance between sample means is the same as variance between individual values divided by sample size. Okay, we multiply both sides with the sample size and change place. Get a formula like that. Variance between individual values equals variance between sample means multiplied by sample size. And that is true if the samples and individuals are drawn from populations that have the same mean. They are drawn from the same distribution, so to speak. Let's make a ratio of those two. But if those two are the same, if we make a ratio of them, of course the ratio will be 1. If you take two values that are of equal size and you make a ratio of them, then you get the ratio of 1. And that ratio we call the F ratio. Variance between sample means multiplied by sample size divided by variance between individual values. And if our individuals that are in different samples, if those samples are drawn from populations with the same mean, then we expect to get this. Then we expect that one to be equal to that one. And in that case, we expect to get the F ratio of 1. If our samples are drawn from populations with the same mean, if the null hypothesis is correct, we expect to get the F ratio that is more or less, that is close to 1. What happens with the F ratio if we draw the samples apart? If we increase the difference between the sample means? What is increased in this formula? The denominator, because then we increase this one. The variance between the sample means. And in that case, the F ratio increases. if you decrease the variance within the samples, like we did in that figure a few slides ago, then again the F ratio increases. And if we increase the sample sizes, we also increase the F ratio. So the larger the F ratio is, the lower the p-value. The larger the F ratio is, the lower is the probability of getting those data we have, given that the null hypothesis is correct. And the nice thing is that we know what F ratio to expect, with what probability if the null hypothesis is correct. So we have this relation between the F ratio and the probability of getting that F ratio, F ratio, or even larger one, given that the null hypothesis is correct. And depends a bit, at least, on degrees of freedom. We'll have a look at that a bit later. So if we, for instance, have 1 and 10 degrees of freedom, that would mean that we have 12 individuals in 2 samples. Okay, so that's our data. We have 12 individuals altogether, and they are in 2 samples. Then it would be this red line here. If we draw 2 samples from 2 populations that have the same mean, and our samples are of size 6, then the probability of getting a F ratio that is larger than 1, or if I say 1 or larger, it doesn't matter, okay, 1 or larger, then that probability is 30%. If the null hypothesis is correct, the probability of getting a F ratio larger than 1 is 30%. The probability of getting a F ratio larger than 2 is 20%. Larger than 3, 10%, and so on. So if we would have 2 samples representing 2 different populations, 6 individuals each in the samples, how large would we demand the F ratio to be before we are allowed to reject the null hypothesis? How large? Of course, you can't see exactly here, but about approximately, that's our significance level. We would require the F ratio to be 5 or larger before we are allowed to reject the null hypothesis. Because in that case, if it's 5 or larger, the probability of getting the data we have, if the null hypothesis is correct, is estimated to be less than 5%. And we are allowed to reject the null hypothesis. So we know the relation between the F ratio and the probability of getting a F ratio that is that large or larger, given that the null hypothesis is correct. And we use that information in order to draw conclusions. When are we allowed to reject the null hypothesis? Okay, variance. The formula for variance looks like this. You take deviations between individual values and the sample mean. You square that difference, and you take sum over all individuals, and you divide by degrees of freedom. That gives you the variance. Nominator, that's called sum of squares. Sum of squared differences between individual values and the sample mean. And this is called degrees of freedom. So variance is the same thing as sum of squares divided by degrees of freedom. If we do a one-way ANOVA, we can calculate 3 different sum of squares. Total sum of squares, between group sum of squares, and within group sum of squares. So let's imagine we have 3 groups here, A, B, and C, and we have 3 individuals in each group. So if we're going to calculate total sum of squares, how do we do that? We do it like this. It's the green lines here. That's the total sum of squares. For each individual value, we take the value minus the total mean, we square that, and we take the sum over all individuals. That gives us information. How much variation is there in this case in life satisfaction among these 9 individuals? The total amount of variation in the dependent variable. This much nuances there are when it comes to life satisfaction in our data set. Between group sum of squares. How do we calculate that? We do it like this. We, so to speak, replace each value with the sample mean. So we replace those 3 values with the sample mean. We replace those 3 values with the sample mean, and so on. And after that replacement, we do the same thing. So for each value, we take the sample mean minus the total mean and square that, and the sum over all individuals. This could be described, this much sum of squares, this much variation would be left if we replaced every individual value with the sample mean. This much of the information, this much of the nuances in life satisfaction would still be there if we would replace every value with the sample mean. This much is explained by group membership, so to speak. If we said that the only thing that matters for your life satisfaction is which of these 3 groups you belong to, this is how much of the variation that would be left. Within group sum of squares, how do we calculate that? It's also called residuals or errors also. Well, it's the stuff that would be lost. It's the variance, the variation that would be lost if we replace every value with the sample mean. So for every value, we take the value, individual value, minus the sample mean, and we square that difference, and we take the sum over all individuals. This much of the variation, in this case in life satisfaction, is not explained by group membership. Because if everything was explained by group membership, then we don't have any within group sum of squares. Then you have the same value if you belong to the same group. If income is completely explained by sex, then you have the same income if you have the same sex. There's no variation within the respective groups. So we could take an example. So we have 4 different groups here. Let's say the patients with depression. So we divide them into 4 different treatment groups. Control, pill group, they get the pill. Cognitive therapy group, and Freudian group here. They get Freudian therapy. And they get their therapy for a while, and then we measure their life satisfaction. We can...
5 1 to 5, what was the grade?
Let's say 1 to 7. That's what I usually use. Okay, so 1 to 7. So of course we have quite a few here with low life satisfaction. A few here are quite happy with their life. Mean for each group: 1.3 for the control group, 3.2 for the pill group, and so on. Total mean, all these values, 24 values, 2.6. Total sum of squares. We take each individual value minus the total mean and square that and sum it. 47.6. That's the diversion in life satisfaction among these 24 individuals. Between group sum of squares, in each row we take the sample mean minus the total mean, square that, and take the sum. 18.8. if we said that the only thing that matters is what treatment you get, this is how much of the variation in life satisfaction that would be left. How much would be lost if we said that treatment is the only thing that matters? Well, the residuals here, the within groups sum of squares. In each row, we take the individual value minus the sample mean, square that, and take the sum here. 28.8. And we see that if we take the sum of those two, between group sum of squares plus within group sum of squares, it's exactly the same as total sum of squares. So the variation here can be divided into two parts. That is explained by group membership, and the part that is not explained by group membership. Okay, let's have a look at the SPSS output here. And of course, SPS is calculated wrong here. No, it didn't. I guess it's due to rounding here. Okay, so now you know. If you would like to calculate with Excel, you can do the same here. Okay, we have degrees of freedom. We have 3 degrees of freedom between groups, and we have 20 degrees of freedom within groups, and 23 totally. So what does this, how do we get these degrees of freedom? Well, with these formulas here. Between group sum of squares is number of groups minus 1. You could imagine to illustrate it like this. We have a total mean, 2.6, and we have 4 sample means. How many of those 4 sample means can vary given that the total mean is 2.6? Well, all but 1. So 3 of those 4 sample means are free to vary. 3 degrees of freedom. Within groups, we have 20 degrees of freedom. Total number of individuals minus number of groups. So in this case, 24 individuals in 4 groups. 24 minus 4, 20. Can you imagine like this? We have 4 sample means. How many of the individual values are free to vary given that those 4 sample means are what they are? Well, in each group, all values but 1. So in the control group, all but 1, 5. Pill group, all but 1, 5. So that comes up to total number of individuals minus number of groups. So 20 of those 24 values are free to vary given that we have 4 sample means. Total degrees of freedom, 23. We have 24 individuals. We have 1 total mean, 2.6. How many of those 24 values are free to vary given that we have a total mean of 2.6? Well, all but 1. 23 of those 24. The sum of between groups degrees of freedom and within groups degrees of freedom becomes the same as total degrees of freedom. What do we do now? We take sum of squares divided by respective degrees of freedom, and we get these values, mean square. So 18.8 divided by 3, 6.3. 28.8 divided by 20, 1.4. Mean square. Do we have another word for that? Sum of squares divided by degrees of freedom? Variance. So this is between groups variance, and this is within groups variance. If the 4 populations that the 4 samples represent, if they have the same mean when it comes to life satisfaction, which is the same as the null hypothesis would be correct, what do we expect of these variances? We expect them to be roughly the same, because that's how the calculations are done. If the populations have the same mean, we expect those to become roughly the same. So now we make a ratio of those. 6.3 divided by 1.4. We get the F ratio. 4.3. And we expect that to be roughly 1. That's the baseline here. Then we get the next value here. Significance level. 0.016. What does it stand for? Well, it stands for, we know the distribution of F values, F ratios, given that the null hypothesis is correct. So in this case, it calculates, with 3 and 20 degrees of freedom, how much of the F distribution is above the value 4.3. Well, that proportion of the F distribution that is above 4.3 is 1.6%. What do we translate that value to? Proportion in a F distribution. An F distribution is a frequency distribution. What do we translate that to? We translate it to a probability. If the null hypothesis is correct, all 4 populations have the same mean, then the probability of getting 4 samples with these characteristics, for instance, these large differences between the sample means, these large or larger, that probability is calculated to be 1.6%. The probability of getting sample means that differ this much from each other, which leads to our F ratio that is this high, if the null hypothesis is correct, is 1.6%. So what conclusion do we draw from this? Your supervisor comes in, has a look at your data. Well, what does it mean? He or she says. What conclusion do we draw from this? And then you say, what do you say? What do we do with our null hypothesis? We reject it, because the probability of getting our data, if the null hypothesis is correct, is so small that we assume that the null hypothesis is false. So we reject it. And if we reject the null hypothesis, what do we say instead? It's significant. What does it mean? What was the null hypothesis?
At least
Yes, the null hypothesis is that all population means are the same. We reject that. So we say that at least two of the populations have means that differ from each other. That's the conclusion. Not all of them have the same mean. At least 2 of them have differing means. That's our conclusion here. Does that sound like a satisfactory conclusion? If you say that to your supervisor, at least 2 of them differ, would he or she say, okay, that's good. See you tomorrow? No, what would he or she ask? Which 2? So the ANOVA tells us there's a difference in this case because it's significant. It's the difference at least between two of the groups. But it doesn't tell us which of them. But of course we want to know which of them differ from each other. So we would go further in order to answer that question. So if we get a significant ANOVA, we want to go further to get more information. How does the differences between the populations look like? So you can do this in different ways. You could conduct something called a priori comparisons, for instance. That means that you have a hypothesis about how the population means would differ from each other. So you could, for instance, have this kind of hypothesis. My hypothesis is that population 1 has the lowest mean. Population 2 and 3 have the same and second lowest mean. And population 4 and 5 have the highest mean. So you could state a hypothesis like this. And then you compare that hypothesis with data. So you have stated this before. This is what I expect. You compare it with data, and either this hypothesis is rejected or not. Get a picture. Does this fit with data or does it not? Something that is more common if you get a significant ANOVA is that you do all the pairwise comparisons. You compare every sample with every sample with something called post hoc test. After the fact. If we have found that there is a difference at least between two of the groups, we do a post hoc test and do all the pairwise comparisons and in order to see between which samples do we have a difference. And there is we have several post hoc tests to choose between. The difference between these is they do the calculations differently, slightly differently. You shouldn't exaggerate. They usually tend to indicate the same thing. But they vary a bit about how conservative they are. Some of them are are more conservative than others. And what does it mean for a test to be statistically conservative? A test is conservative if it requires big differences before it says it's significant. That's a conservative test. Does it sound like a good thing? Well, it decreases the risk for type 1 error. With a conservative test, the risk for type 1 error is lower. The risk of saying that there is a difference when there actually is no difference becomes lower. What is the downside of a conservative test? Lower power. Because it's increased likelihood that you miss a difference that actually exists. So lower power, lower risk for type 1 error, but at the same time lower power. More liberal tests, I don't know, I guess I got these expressions from somewhere. More liberal tests, increased risk for type 1 error, but at the same time higher power. And the most liberal of these post hoc tests, you kind of notice that from its name, is the Fisher's least significant difference, LSD. It's very liberal. It's like conducting multiple t-tests. It's the same thing. So increased risk for type 1 error, but at the same time high power. Okay. Some say, I read this from a book written by a statistician called Howell, and he said that this should not be used if there are more than 3 groups. Then we have another one here, Tukey honest significant difference it's called. It supposedly corrects the algorithm, the calculation, in order for the type 1 error for every comparison is never higher than the significance level. So it's maximally, for every pairwise comparison, the risk for type 1 error is maximally the same as the significance level. Okay. According to Howell, this might be a bit conservative. The Tukey was, but it's very popular. In psychology, we always use this as our post hoc test. Which I think, at least partly, it's because HSD is honest significant differences. So it sounds good. Okay, that one nobody uses because you can't pronounce it. But Tukey said those are the names of various statisticians. That's recommended by Howell. He recommended it. I'll present one more here. Sheffier It's the hardliner's favorite. It's the most conservative of these. Well, I guess you can make an even more conservative if you would like to. I read somewhere that if you have very different sample sizes, so your samples are very different in size, then it might lead to increased risk for type 1 error, and therefore you should adjust for this somehow. And one way to do it is using this Sheffier because it's conservative. I don't know. I haven't made any simulations in order to see if that is correct. Okay, so there are a few post hoc tests to choose among. And again, we shouldn't exaggerate the difference. Usually they indicate the same thing. So it's not, your result doesn't become something very different depending on which post hoc test you choose to use. The more significance tests you do with the same significance level, then there's an increased risk that you will, by chance, get at least one significant result that is due to chance. And therefore, there's increased risk for type 1 error. Let's say you do a t-test. You compare two groups, and you have the significance level 5%. It's supposed to do that there's 5% risk for you to say that there is a difference when there actually is no risk for type 1 error. Imagine you do the same t-test for different groups 100 times. If the risk for type 1 error is 5% in each of them, of course there's an increased risk that you will conduct a type 1 error at least once when you do more tests. So sometimes it's recommended that you adjust your significance level according to how many tests you do. There's something called, well, the most crude one, it's called Bonferroni correction. You can get to Bonferroni post hoc test also, which says that your significance level that you should use is your original significance level divided by number of tests. So if you have an original significance level of 0.05 and you do 10 different significance tests, then you should use not 0.05 but 0.005. I don't do it like that. Well, sometimes if I have a very high power in my database, because of course you decrease your power in the analysis if you're going to do like this at the same time. There are more complex ways to adjust for number of tests also. And of course, if you want to be a smart Alec, you say, hey, am I supposed to divide by all the significance tests I do in all my life? Or is it only those I do in this study? So by now I conducted maybe 200,000 significance tests. Should I buy it down to significance level 0.00000000000 and so on? So it's a favorite of reviewers. You come across that. Oh, you do several tests. You should correct for this. And of course, then you might do it. At least if the results remain significant, even with the correction. Yeah, post hoc test. Otherwise, of course, not Fisher's doesn't care about it. It's like conducting several t-tests. You get the same result. You get the same p-values as if you would do every single pairwise t-test. But for instance, Tukey here, it corrects for it somehow. So it's more conservative than conducting several t-tests. So it tries to correct for this. And Sheffier corrects even more. Of course, if you only have two groups, then there's no reason for post hoc test. Because if you find there is a difference at least between two, well, then you know where it is. It's between those two. But if you have more groups, yeah, of course you want to know between which groups do we have the difference. The sum of squares you calculate, you can do it differently. there's something called type 1 sum of squares. That is affected by unequal sample sizes. What we usually use is instead something called type 3 sum of squares. And that one is not affected by unequal sample sizes to that degree. Of course, you could try different variations. You have a look at Sheffier and so on. See, of course, you want, if you do a different test, them to indicate the same thing. Then you can rest assured that my results is not due to something strange in the data. It's robust. Because there's not always a clear answer. You do it like this, not like that. So what I usually recommend, well, try different ways to do your analysis. If you get different results, well, then you should be a bit careful. But if the different ways of analyzing your data indicate the same thing, well, that's a good. Then rest assured, it's not due to strange things in your data that you get the results. There are some assumptions behind the calculations here. So the ANOVA calculations, they are based on some assumptions. For instance, that we have homogeneous variances. So that the variance on the variable, the dependent variable in question, is the same in all populations. So in the populations, we don't want to have large variance in some population and small variance in some. Because then the algorithm doesn't function as it's supposed to. It's based on this assumption. And also that the variable is more or less normally distributed in all populations. That's also an assumption that the calculation is based on. If those are not fulfilled, we can't trust our results as much. And also the third point, the observations are independent. Well, in this case, I shouldn't maybe use the word independent again. For instance, you can't have if you have you have depression as your dependent variable. It's not good if you have married couples in one of your samples, that some of them are married with each other. Because you can assume that there's an association in level of depression within married couples. I guess there is some. If one of them is high in depression, it probably has an effect on the depression of the spouse. And if you treat them as independent individuals, you might go wrong. Because in that case, what this tends to lead to, we can't be sure of this, but what this could lead to is that you have decreased variance in that sample. Because you have a few values that are more close to each other than you would expect them to be if the values were from independent individuals. And if you have decreased variance within the sample, you have increased risk for type 1 error. You would have larger variance within the sample if you had independent values within the sample. So what do we do if we can't assume this, that these factors are fulfilled? Well, if we don't have homogeneous variances, we could, for instance, conduct something called robust equality of means test. And in SPSS, we can easily get two of them, Welch and Brown-Forsyth. So they analyze the same thing. Is there a difference in mean between the populations, but without an assumption of homogeneous variances? Then you might, of course, ask, well, why do we use ANOVA? Why not use this one if they test the same thing but without the assumption of homogeneous variances? Well, it's a good thing that they don't have this assumption. What do you think is the downside of Welch and Brown foresight compared with ANOVA? There is no such thing as a free lunch. So if they don't have this assumption, downside is they have lower power. So if the assumptions are met, ANOVA function as it's thought supposed to, it has higher power than those tests. But of course, it's satisfactory if ANOVA and those indicate the same thing. If your variable is not normally distributed, of course, if you have small samples, you will never see that your variable is normally distributed within the sample. But this is an assumption about how it looks like in the population. You can test if your distribution differs significantly from a normal distribution. There are a few tests for that. There's something called Shapiro-Wilks, for instance, that you could test the distribution with. If you find that my variable, my dependent variable, is not normally distributed, well, you could try with some kind of transformation of it. If you have a positive skew, for instance, you might try with the logarithmic transformation. You take the log of the value instead of the original value, because positive skew tends to become less with the logarithmic transformation. It might help. Or there are some non-parametric tests, for instance, Kruskal-Wallis, close at hand. You could test that instead. Of course, you might do both ANOVA and Kruskal-Wallis and sleep well that night if they indicate the same thing. If your observations are not independent, you find out, oh no, I have a lot of married couples within my samples, so you have subgroups within the samples. Well, maybe you could try to analyze this with multi-level modeling instead of with ANOVA. Then you try to control for the fact that you have dependence between your values. So you put in, for instance, married couples as one level in your data and try to control for this fact. Couple of words here. If you do this in SPSS, it's ask if your independent variables are fixed or random. So you have to make a choice here. The rule of thumb is that if you don't know, it's fixed. Okay. So let's say we want to analyze, is there a difference between the average level of depression between different countries in the world, or can we assume that the average level of depression is the same in all countries? Okay, so you're going to compare countries with each other. And what do we have? 200 plus countries in the world. You think, oh, I can't have data from all of them. So what do? What is the best way to do? You think I have enough money to collect data from 10 countries. How do you choose your 10 countries? From the population of 200 plus countries. You could do it randomly. So you take a random sample of countries from the population of all countries. Then you have a random factor. If you just think, oh, I'll take a few countries close by here. I take Sweden. Oh, I'm going to Spain on holiday, so I collect some data there also. And I have a friend in Hungary. I collect some data there. And you just take a few countries like that. It's not a random sample. And then you compare the countries with each other. Then you have a fixed factor. It's not the levels of the factor has not randomly been chosen from the population of all possible levels. If you want to compare the effect of a drug on something, on health, so you have groups that get the drug, different amounts of the drug, and you think, well, you could get somewhere between 0 and 100 milligrams. After that, the risk of dying is too high. So you think, I can choose 5 groups. So you pick randomly 5 levels from all levels from 0 to 100. Then you have a random factor. If you just decide, well, I have 0, 10, 20, 40, you just make that kind of decision, not randomly chosen. Then you have a fixed factor. That affects how the calculations are conducted. So we're going to stick with fixed factors. I guess that's the most usual. Effect size. That's also one popular thing among reviewers. You should. I also, when I do a review, I start off. I don't even read the paper. I just write. You should report effect sizes. Okay. Not only p-values. And the effect size, if we have a one-way ANOVA, it stands for how much of the variance in the dependent variable can be explained by group membership. And we can calculate this in a few ways. We have something called the eta squared, for instance. You calculate it by taking sum of squares between groups divided by sum of squares total. So you get that as a percentage. Okay, we're going to talk about regression analysis on Thursday, and the most common effect size, well, you get something called R squared in regression analysis, and this is the same thing. And this is biased. This is biased. It gives you a higher number than you actually should get. It's positively biased. So people have tried to adjust for that, to come up with a calculation of effect size that is not biased. And we have something called omega square that is less biased. Doesn't overestimate the effect size to the same degree as eta squared does. In regression analysis, you get something called adjusted R square. And it's similar to this. So if we have a look at our data, our 4 groups, 4 treatment groups, and level of life satisfaction in the different groups, if we calculate eta square here, we get 39. It says that 39% of the variance in life satisfaction is explained by which treatment you get. 39% of the variance in the dependent variable can be explained by group membership. If we calculate this omega square instead, it becomes somewhat lower. It says we have 29% variance. We come to two-way ANOVA for independent measures. You see that's two-way ANOVA? So we have 2 independent variables. So it could, for instance, be that people get different treatments and they have differing sex. So every person belongs to one combination of sex and treatment. Okay, that's called factorial design. So what we get here, a few words about effects here. So if we, for instance, have treatment and sex as our independent variables, and we have depression as our dependent variable, we put them in a two-way ANOVA, then we get 3 effects. We get main effect of treatment, we get main effect of sex, and we get treatment by sex interaction. What is a main effect? What is the main effect of treatment, for instance? Well, it's like we don't care about what individuals have, what sex they have. So we collapse data over sex and have a look at how does the mean level of depression differ between the different treatment groups. And if it's significant, we say there is a difference between at least 2 of the treatment groups when it comes to average level of depression. So it's like not having sex in your analysis. That's not completely true, but that's how we interpret the results. The main effect of sex, we don't care about what treatment people get. We compare, is there a difference between average level of depression between men and women? Main effect. Simple effect is somewhat different. So if main effect is effect of one independent variable over all levels of the other independent variable, simple effect is the effect of one independent variable for a specific level of the other independent variable. So we could calculate, for instance, the effect of treatment on level of depression only for women. Then we get the simple effect of treatment among women. And we can calculate the same thing separately for men. The effect of treatment only for men. The simple effect of treatment for men. Did you get the difference here? Main effect, the effect of one independent variable for over all levels of the other one. Simple effect, the effect of one independent variable for a specific level of the other independent variable. Then we can use that phrase, simple effect, to define an interaction. If the simple effect of one independent variable is different for the levels of the other independent variable, then we have an interaction effect. If the effect of treatment on depression is different for men and women, then we have a treatment by sex interaction. And interactions always go into both directions. So if the effect of treatment on depression is different for men and women, that means at the same time that the effect of sex on depression is different for the different treatment groups. If A and B interact in their effect on C, it means that the effect of A on C looks differently depending on the value on B, but at the same time that the effect of B on C looks differently depending on the value of A. No, regression analysis and variance analysis is exactly the same. It's called general linear model. All results you can get here, you could also get with the regression analysis. It's exactly the same algorithm in the bottom. So let's have a look here. So we have female and male patients, and they get either treatment A or treatment B. So we have 2 by 2 here. So it becomes 4 groups. And we measure life satisfaction. We have 3 individuals in each group, and we measure the life satisfaction. And we get data like this. So we can calculate a few sum of squares here again. Total sum of squares, the same way as before. We take every individual's value, minus total mean, square that, and sum over all individuals. The variation in life satisfaction among these 12 individuals. Sum of square for the effect of sex. It's what we would get if we replaced every individual's values with the mean for his or her sex. So we say we replace all these female values, these 6 female, we replace with that one. And we look how much it differs from the total mean, square that difference, and take the sum. And we do the same for our 6 men. We replace their value with the mean for all men. If it looks like this, like it does in this example, does it indicate that sex is important for life satisfaction? Is there a big difference between men, female, and male means? No, it's not a very large difference here. It's more or less the same. Right? So not much of a main effect of sex on life satisfaction. Treatment sum of squares. I know this doesn't, but then we would replace every value, individual value, with the mean for that treatment group. So those who get treatment A, we replace with the mean for treatment A. And look how much it differs from the grand mean, the total mean. Square that difference. If you get treatment B, we replace the value with the mean for treatment B. And take the difference from the total mean, square that difference, and then we take the sum over all individuals. If it looks like this, which is more important, sex or treatment? For life satisfaction? Treatment, because there is a larger difference between the means for treatment groups than for the means between men and women. We can calculate one more. I call it cell sum of squares. And cell is the combination of all independent variables. So if you belong to the same cell, you have the same value on all independent variables. So in this case, our independent variables are sex and treatment. So if you have the same sex and the same treatment, then you belong to the same cell. So those three belong to the same cell, and so on. So we have 4 cells here. So the cell sum of squares, so to speak, we replace every value with the mean for the cell. And then we take how much it differs from the grand mean, the total mean, square that difference, and take the sum over all individuals. Cell sum of squares. This is how much would be left if we said that the cell you belong to, the combination of independent variable values, explains everything. We have one lost sum of squares. Can you guess what it's called? Residual or error. I think it says error in SPSS output. Residual is quite common name also. So we take every individual's value minus the cell mean and square that and take the sum over all individuals. It's what would be lost if we replaced every value with the cell mean. Now we have to calculate some more things. Sum of square for the interaction. How much of the variation in the dependent variable can be explained by the interaction? By the interaction between the two independent variables. We have variation between the cells. And the cell here is the combination of sex and treatment. Why do we have variation between the cells? What could have caused the difference between the cells? It could have been caused by sex. Right? Difference between the cells could have been caused by the people in different cells have different sex. It could have been caused by treatment. And it could have been caused by the interaction between sex and treatment. Nothing more. The difference between the cells is the sum of those 3 things. Effect of treatment, effect of sex, and their interaction. So now we, so to speak, go the other way around here. So we take differences, sum of squares between the cells, and we take away whatever can be explained by sex, and we take away whatever can be explained by treatment. And whatever is left here must be explained by the interaction between treatment and sex. So that's how we calculate sum of squares for the interaction.
Here's another example of how to calculate the two-way ANOVA, now with actual numbers. So in A column here we have people in 4 different treatment groups. We have a control group, we have a pill group, we have a cognitive therapy group, and we have a dynamic group. But also, and we see this in column B, the patients here, they belong to 2 different age categories. Gammal, that means old, and ung, that means young. So 2 different age groups. Column C, we have the degree of life satisfaction. So let's say we have a scale from 1 to 7. So this is each individual's value on the dependent variable. Column D, it's the mean for the treatment groups. So for everybody in the control group, in that line, they have a value of 1.33 because that's the mean in the control group. 3.17 in the pill group, 3.67 in the cognitive group, and 2.3 in the dynamic group. Column E, that's the mean for the 2 age categories. So in each line, if the person in question belongs to the older category, they have the mean of 2.5. And in each row, if the person is a young one, they have a mean of 2.75. Column F, that's the cell mean. So for each combination of treatment and age category. So the three first persons, they are old patients in the control group. They have 1.33. That's the cell mean. The same cell mean we have for the young ones in the control group. We have 4 for the older ones in the pill group. 2.33 for the younger patients in the pill group, and so on. So in column F, in each row, we have the mean for the cell that the person in that row belongs to. Column G, that's the total mean, 2.63. And then we calculate our sum of squares. So in order to calculate our total sum of squares, we take in each row the individual value, the individual person's value, minus the total mean, which we have in this G column. We take the difference and we square that. We do that in each row, and we get the sum 47.6. So that's a measure of the variation in life satisfaction in this sample, in the total sample. Next column, difference between the D and G columns squared. And in the D column we have the treatment mean, and in the G column the total mean. So what we get here is the sum of squares that can be attributed to treatment. So we do that in each row, and we square it, and we sum it, and we get 18.9. So this is a measure of how much of the variation in life satisfaction is due to treatment. If we would assume that people who get the same treatment have the same level of life satisfaction, this is how much of the variation in life satisfaction that would be retained. Next column, the difference between the E and G columns. And in the E column we have the H mean. So for each individual we take the mean for that person's age group minus the total mean. We square that difference, and we do this in each row, and we take the sum. 0.4. So that is a measure of how much of the variation in life satisfaction would be retained if we assume that everybody of the same age have the same level of life satisfaction. So very little. How come it becomes so low, this number? Well, it's of course because the difference between the two means of the two age categories, 2.5 for the older ones and 2.75 for the younger ones, that difference is very small. So very little of the variation in life satisfaction is due to differences in age. Next column, there we have the difference between the F and G columns. And in the F column we have the cell mean. So the cell mean in this case is the mean for the combination of treatment and age category. So in each row we take the cell mean minus the total mean and we square that. And we do this in each row and we take the sum. 33.7. In the last column we take in each row the individual person's value in the C column minus the cell mean in the F column. We take that difference, we square it, and we do this in each row and take the sum. That's 14. That's our residual sum of squares, our error sum of squares. It's the sum of squares, it's the variation in life satisfaction that can be explained neither by treatment, neither by age category or their interaction. At the bottom we see the calculation of the sum of squares that is due to the interaction. And the variation in life satisfaction that is due to the interaction between treatment and age category is the differences between the cells that cannot be explained by treatment and neither by age. So the sum of squares for the cells is 33.7, and we take minus whatever can be explained by treatment, 18.9, and minus the amount that can be explained by age category, 0.4. And what we have left here is 14.4. So that is the sum of squares that is explainable by the interaction between treatment and age category. Total sum of squares equals the sum of squares that can be explained by treatment and plus whatever can be explained by age category plus whatever can be explained by the interaction between treatment and age category plus what cannot be explained, the residual sum of squares.
Okay. No, I jump to this output instead. Let's start here. Error, residual. Not explained by sex. Variation in life satisfaction that is neither explained by sex, treatment, or their interaction. It's the variations within the cells. 14. Okay. We have error degrees of freedom, 16. That equals total number of individuals minus number of cells. In this case, 16. We could imagine like this. We have, what do we have? We have 12, in that example, we have 24 individuals in 8 cells. Okay, so we have 8 cell means. How many of those 24 individual values are free to vary, given that we have 8 cell means? Well, all but one in each cell. So 24 minus 8, 16. So sum of squares error sum of squares 14, error degrees of freedom 16. We divide the sum of squares with degrees of freedom, and we get the error mean square, 0.9. Error variance. H, if we sum of squares that can be explained by H, and we have two H groups here, 0.4. We have 1 degree of freedom because we only have two H groups. So we divide sum of squares with degrees of freedom. We get mean square. Now we take this mean square for the effect of H divided by error mean square. So 0.4 divided by 0.9. We get the F ratio for the effect of H. 0.4. If H doesn't matter, if H has no main effect on life satisfaction in this case, what do we expect that F ratio to become, more or less? 1. So in this case it became even lower than 1, 0.4. And we get a p-value, 0.5. What does it actually stand for? 0.5 here. It's a proportion of the F distribution that is above the value 0.4. But we translate it to a probability. The probability of getting this big difference between the H group means, if the H group means in the population do not differ from each other, that probability is 50%. So what do we say about the effect of H on life satisfaction? Will we say that there is an effect of H on life satisfaction? No. This effect is not significant. The probability of getting this small difference, even if there is no difference between the population means, is so high, so we can't with enough confidence reject the null hypothesis. We retain it. So no main effect of H. How about treatment? If we collapse data over the two H groups, will we assume that treatment has any effect on life satisfaction? Yes, because our p-value is lower than the significance level. It's lower than 0.05. So the probability of getting these big differences between the treatment group means, if there are no effect in the population of treatment, is so low, so we assume there is an effect of treatment. At least two of the treatment groups have differing level of life satisfaction. And lastly, and most interestingly, what conclusion do we draw? H by treatment interaction. And it's significant. What does that mean? We just concluded there is an effect of treatment on the average level of life satisfaction. But what? Yes, the effect of treatment looks different for female and male patients. That's what the interaction says. Okay, would we be satisfied with this? We stop there, right? That's enough. We stop there. We know enough now. Or?
But H also treatment interaction.
Yeah, sorry.
Not sex, age.
Not sex, age. I confused them also. I should stick to the same all through. So it's age by treatment interaction. So we satisfied with that? Yeah. In what way does the effect of treatment differ between older and younger patients? How do we do that? Well, we could have a look at the simple effect of treatment separately for younger and older patients. Because the interaction indicates that simple effect looks different. So we could do that. Simple effect. So this is younger patients, only younger patients, and this is only older patients. ANOVA, post hoc, Chuki post hoc. So is there any effect of treatment on life satisfaction among younger patients? Yes. What number does? Yeah. So what does that mean? What conclusion do we draw? Among younger patients there is. Yes, what exactly does that mean? At least between 2 of the 4 treatment groups, there is a difference in average level of life satisfaction. Of course, that's not completely satisfying either. So we have a post hoc test here. So here we have every pairwise comparison. And just to be sure, we even have them twice in both directions. So it works like this. Here we have control group. Control group compared with the pill group. Mean difference -1. It means that among younger patients, the average level of life satisfaction in the control group is 1 point lower than the average level of life satisfaction in the pill group. That's why it's negative. Control minus pill is -1. Is that difference significant? No. So we will not assume any difference between control and pill group among younger patients. Control compared with cognitive therapy. Mean difference -3.7. So the mean in the cognitive group is 3.7 points higher than in the control group, and it's significant. And so on. Control compared with dynamic therapy. No difference. And so on. So all pairwise comparisons. And if there will always be one of these boxes with only positive values. And in this case, it's cognitive compared with rest. It means that the mean is highest for the cognitive group, significantly higher than for the control group, and marginally significantly higher than the 2 other treatment groups. So cognitive therapy, the best for younger patients, significantly better than the control condition. How about older patients? Is there an effect of treatment? Nothing is good for older patients. Is there an effect of treatment? Because it might be that there is no effect. Is there any effect? Yes. And then we have a look at our post hoc test. Which group is the best for older patients? The pill group. Only positive differences. So the pill group has higher average level of life satisfaction compared with the control group. And marginally, the data became a bit strange here. Marginally significantly higher than for cognitive and dynamic groups. So for younger patients, cognitive therapy is the best. For older patients, the pill is the best. I hope nobody, I just made this data up. Well, we could look in that way if we want to. We could split the file from treatment and have a look at the effect of age for the different treatments. For which treatment is there a difference between life satisfaction between older and younger patients? For cognitive and none of the others. Can you guess what the p-value of 1 means? The difference between the sample means is 0. They have exactly the same mean. That's the only situation the p-value becomes exactly 1. So with a figure like this. Of course, if you have an interaction, I'll have a word about that also. If you have an interaction and you're going to have a look at simple effects, you have to make a, well, you could do both, but usually you choose one of the ways to stratify data as you express it. So if we have a treatment by age interaction, we could look at the effect of treatment separately for age groups, as we did, or the effect of age separately for treatment groups. Which seems more rational? Do you have any feeling for that? I know what I would prefer. I know exactly what I would prefer. I would prefer to have a look at the effect of treatment separately for young and older patients rather than the other way. Why? Well, what are we going to have these data for? We're going to have a look, what kind of treatment should we give to different patients? And we can't decide what age patients will have. They have the age they have. We can't affect that. But we can affect what treatment they get. So we want to come up with some kind of rule. If you get the younger patients, give them this treatment. If you have older patients, give them this treatment. Therefore, it seems more rational to look at the effect of whatever you can manipulate for different levels for whatever you can't manipulate, rather than the other way around. Because we can't take people in, or you get cognitive therapy. Well, then I decide that you will be a young patient. A last word about two-way ANOVA here. We have the treatment groups, 4 treatment groups, and life satisfaction for 24 patients. And I didn't change that from the one-way to two-way ANOVA. I kept them, the treatment variable and the life satisfaction variable, exactly the same. I just added the age variable. Okay, so let's have a look here. That's the first one-way ANOVA. Between group sum of squares, 18.8. The effect of treatment in this analysis, exactly the same sum of squares. Because the sample means are exactly the same. So the variance between the sample means is exactly the same in both situations. We have 4 groups, so we have 3 degrees of freedom. And therefore, we have the same variance here, 6.3. So it's exactly the same, because the sample sizes and the difference between the sample means is exactly the same. But what happens in the next step? The F ratio, 4.3, the F ratio, 7.2. Might not seem as a very large increase, but still. And therefore, because the F ratio increases here, we have a lower p-value here than there. We have a more significant effect of treatment here compared with there, although the difference between the treatment group means is exactly the same. How come? What has changed? Yes, we have not very big, but some difference between the age groups. In the first analysis, we don't include age in the model. So what is the difference between the age groups treated as in the first analysis? Where does the variance that depends on age, where does it end up? Within groups. Yes, it's included there. Everything that is not due to treatment is treated as within groups as error variance. Here, although the effect of H is not very big, still it explains a little bit of the variance. And therefore, the error variance decreases. And much more so because we have some of the variance in life satisfaction, well, quite a bit of it, well, some of it, is explained by the interaction between treatment and age. And in the first analysis, because the interaction age treatment is not included in the model, it becomes error variance. It's included in the within groups variance. So what happens here is that the error variance, 14, is smaller than there, 28. And although we have less degrees of freedom here, the error variance is still smaller here, 0.9, compared with the error variance here, that's called within, 1.4. And because that's in the denominator, when we calculate the F ratio, in this case, the F ratio becomes higher than in that case. And the p-value becomes lower. So that's quite often you see like that. The effect of something, an independent variable, becomes clearer if you have control for other variables. Okay, multi-way ANOVA. You see it's a multi-way? So, a few words about this, multi-way. I don't know what the official lower limit for multi-way is, but I guess one-way, two-way, multi-way, three-way, four-way. They become more and more complex, these models, the more independent variables you have. If we have two independent variables, as we looked, then you get two main effects and one interaction. One two-way interaction. Two-way interaction because it's the interaction of two independent variables. If we have three independent variables, A, B, and C, then we get three main effects, one for each independent variable. We get three two-way interactions, A by B, A by C, B by C, and one three-way interaction, A by B by C. Four independent variables, then we're up to four main effects. We have 1, 2, 3, 4, 5, 6 two-way interactions. We have 1, 2, 3, 4 three-way interactions. And that's the grand finale here, four-way interactions. There are a few papers I come across with a three-way interaction that makes sense, but after that, at least I can't follow what four-way interaction. Try to describe that. You need 4 pages of text to describe it. You get very in the end you get very small cells, and therefore you get low power for various effects. So it's quite common if you want to have for instance, three independent variables, you have a look at the full model. So with all three two-way interactions and the three-way interaction. If the three-way interaction is non-significant, you take it away from the model. You make the model simpler. So you delete interactions on a higher level if they're not significant, in order to make the model simpler. Okay, we have a look at the output here. So we have sex, age, and treatment. 3 two-way interactions and 1 three-way interaction. And what do we say about the three-way interaction here in this case? Significant. So we have a sex by age by treatment, significant three-way interaction. What does that mean, that we have a three-way interaction? What is the meaning of a two-way interaction? In the last example, we found the age by treatment interaction. What does that mean? Yeah, exactly. The effect of treatment looks different for older and younger patients. If we have a three-way interaction, what does that mean? It means that the age by treatment interaction, two-way interaction, the age by treatment two-way interaction looks different depending on what sex you have. So a three-way interaction means that a two-way interaction looks different depending on what level you are on the third independent variable. That's what the three-way interaction means. The corrected total is the cell sum of squares. So you take, in this case, we have 8 cell means. So you take the cell mean minus total mean, square that difference, and multiplied by number of individuals. So it's the difference between the cells. The intercept sum of squares here, then you take every individual value minus 0. So it's minus nothing. So those are not what it's if you're going to have the intercept in your model or not. If you're going to, so to speak, compare with the value of 0 or not. Usually it's not done like that. We calculate the sum of squares in relation to the total mean, not in relation to 0. Okay. So in this case we have a significant three-way interaction between sex, age, and treatment. How would we continue? Well, we could, for instance, split the file, have a look at the interaction between age and treatment separately for men and women, or maybe the interaction between sex and treatment separately for younger and older patients. So you split the file from one. You stratify. So in this case, I stratified from sex, so women and men, and this is what the two-way interaction between age and treatment look like for female patients and for male patients. So for female patients, if we interpret, we could go even further to get every single p-value here. But the figure here indicates that for female patients, it's better to get cognitive therapy compared with dynamic therapy if you're young. If you're old, it doesn't matter. Then the type of therapy doesn't have any effect on your life satisfaction. Does it sound realistic? No. I just made the figures up. While for male patients, how do we describe the results for male patients? You should be old. You should be old. It doesn't matter what therapy you get as long as you're old. So that's what it indicates. So obviously the two-way interaction between age and treatment looks different for male and female patients. That's why we have a significant three-way interaction. If we split from the other way, we split from age and have a look at sex by treatment interaction, it might look same. Maybe. So if you get a significant two-way interaction or not might depend on which variable you use to stratify your data. Okay, enough said about that. Now we come to dependent measures, repeated measures. Of course, repeated might be a better name because then you know what it's all about. You measure the same individuals on more than one occasion. So every individual has more than one value on the dependent variable. Does it sound like a good idea to measure your individuals on more than one occasion? Yes. You usually get higher power with the analysis like this. because then you can adjust for individual variation.
At the same occasion or different occasions?
No, you have to have several occasions in order to adjust for individual variation. I'll try to illustrate this. So let's say we have a group here, A, B. Okay, let's take a simple example. So we have life satisfaction. Here we have one individual with the value 6, high in life satisfaction. And here we have one individual with value 2, low life satisfaction. What might the difference between these individuals, what might be the cause of the difference between these individuals? Why is that person higher in life satisfaction than that person? And they receive different treatments. What might be the cause here? Well, one possibility is the effect of treatment. That person is higher in life satisfaction because it gets this treatment, while that one gets another treatment. Is there some other possible reason for this difference? Well, maybe this person is, generally speaking, higher in life satisfaction than that one. So it's possible if we change their place, they receive the opposite treatment, we get the same. Oh, now it's treatment B that is better than treatment A. So if we measure each individual only once, in different conditions, the difference between them might be due to individual variation or the effect of treatment. And we can't separate those from each other. Of course, we try to separate them by have random assignment to different conditions, and we hope that the individual variation will take each other out. So that, so to speak, the average level on the dependent variable is the same in both groups before we apply our treatment effect. But we can't be sure about that if we only have one value for each individual. But imagine we measure all individuals twice. So one with treatment A and one with treatment B. And we see for this individual it has value 6 there and value 5 there, and this individual has value 2 here and value 1 there. What does this indicate? This person 1, seems to be, generally speaking, more satisfied with life compared with person 2. And now we have but stronger evidence for that, because there is a difference between them in both conditions. But the data also indicates that treatment A might be slightly better than treatment B, because both of them have higher life satisfaction in treatment A than compared with treatment B. So in this way, when we have more than one value per individual on the different conditions, we can separate the effect of treatment of condition from differences that are due to individual variation. That we cannot do if we only have one value for each individual. If we only have one value for each individual, where does the variation that is due to individual variation, where does it end up? It ends up as error. While here we can calculate how big portion of the variation is due to individual variation and adjust for that. It doesn't end up in the error variance. And therefore we have stronger power here in an analysis like this. Of course, sometimes it's not possible to measure individuals on several occasions. You don't have a setup like that. I'll show that to you with data in a moment. Assumptions. The dependent variable is normally distributed in all populations. Well, no. The extra stuff we have an assumption of sphericity. What is that? Well, it's homogeneous variances for all possible differences. And I'll show you an example. So imagine we measure a few individuals on 3 different occasions here. Time 1, 2, and 3. If we have 3 different measurement points, we can create 3 different differences. So the difference between time 1 and time 2, difference between time 1 and time 3, and difference between time 2 and time 3. If you have 4 occasions, you can create 6 differences. So what this assumption of sphericity says, that the variance on these difference variables are the same in the population. So the variance on this one is the same as the variance on that one, is the same as the variance on that one. The algorithm used to do the calculation is based on this assumption. There is a test, and this time we even don't have to tick a box. You get it automatically. It's called a mock list test of sphericity. Okay, let's have an example here. So we have 8 persons with migraine, and we measure them on 3 occasions. Week 0, baseline, 1 and 2. After 1 week of treatment, after 2 weeks of treatment. So level of migraine on the different occasions for the different individuals. We can calculate the personal mean. So individual 1 over the 3 weeks have a personal mean of 12. Person 2 has an individual mean of 11, and so on. The average, the mean for each week, 22 for week 0, 9 for week 1, and 5.5 for week 2. So the week mean, week average. Okay, total mean, 12. Total sum of squares, we take each value, migraine, minus total mean, square it, take the sum here. Sum of squares that can be explained by individual variation. We take each individual's mean minus total mean, square it, and take the sum here. This much can be explained by individual variation. This we could not have done if we had only one value for each individual. But now we can. Sum of squares that can be explained by week. We take the week in every row, the week mean minus the total mean, square it, and take the sum here. Now we can calculate some more here. Sum of squares for the interaction between person and week. We take the total sum of squares minus whatever can be explained by individual variation, minus the part that can be explained by measurement point, by which week it is. And what we have left here is our interaction. It's due to the interaction between person, individual, and week. So it cannot be explained by what individual the data comes from and what week it is. So it cannot be explained. So it's the same as our error sum of squares. So if we have a look at the output, we'll have a look at mock-list test later. It tells us if we can assume sphericity or not. Depending on that, we can look at different rows here. But let's assume we can assume sphericity here. So we have error variance here. Error sum of squares cannot be explained by individual or what week it is. We have 14 degrees of freedom for that. And error variance. We assume sphericity. We have a sum of squares for the effect of week. 2 degrees of freedom because we have 3 measurement points. So we get 2 degrees of freedom. variance. Variance explained by which week it is. We take the ratio of those two and we get the F ratio. And it became excessively large here. What conclusion do we draw from this? What conclusion do we draw from this? What do we expect it to be? What is the null hypothesis? We measure individuals on 3 weeks. We want to see if there is any change in the level of migraine between the 3 weeks. What does the null hypothesis say? There is no difference. The average level of migraine is the same for all 3 weeks. What do we do with that null hypothesis? Reject it. Exactly. At least 2 of the weeks have differing means on level of migraine. That's exactly the conclusion. Unfortunately, you can't do like there is kind of post hoc tests for repeated measures, but not in the same way as for independent measures. But we can have a look at something called contrast, for instance. Then you have a look at that. Is there a change from the first to the second measure, from the second to the third measure, and so on? I said here, we have higher power because we can calculate whatever is due to individual variation and remove that from the error variance. Let's imagine we do like this. Now we have 8 persons. We measure them at 3 weeks. Imagine we had the following data instead. That week 0 is one group of 8 individuals with the same data here. Week 1 is another group of 8 individuals. And week 2 is a third group of 8 individuals. So the same data, but we treat it as 3 separate groups instead of measurement of 8 individuals on 3 occasions. And let's see how the results differ. So this is what we got now. F value 128 and highly significant. Here is what we would get if we treated it as 24 individuals in 3 different groups instead. You see the sum of squares is exactly the same. The degrees of freedom is exactly the same. The mean square is exactly the same. But the F ratio is much smaller here. It's still very significant, but of course, it's excessively high here. Why? Well, it's because here the error variance is 4.6, where here it's 18. Because here the variance that is explained by individual variation is included in the within groups, in the error variance. While here we can calculate it and separate it from the error variance. So we have higher power with the repeated measures design than with the single measurement design. Last one, mixed ANOVA. You see it's mixed? You Google on mixed up animals and you see what you find. So mixed. We have a mixture of between and within. We measure each individual on several occasions, 2 or more occasions, and they also belong to different groups. So what we get here, if we have 1 between and 1 within. So let's say we have treatment, for instance. We have patients, they get 1 of 2 treatments, treatment A and B, and then we measure them on, let's say, 3 occasions. Baseline after treatment and 1 follow-up. So what effects do we get? We get 3 effects. The effect of time. Is there a change over time? Is there a difference between at least 2 of the time points? What more effect do we get? The group. In this case, it will calculate a mean for all 3 occasions and see if there's a difference between the groups when it comes to the mean on the dependent variable. So collapsed over all time points, is there a difference between the 2 treatment groups? That's the effect of treatment group. And the third effect is treatment time interaction. Exactly. So, sum of squares. Sum of squares for the interaction. You take sum of squares, that is differences between your cells, and the cell here is the combination of group and time point. And you subtract whatever can be explained by the group and whatever can be explained by time. And what you have left is the sum of squares explained by the group by time interaction. Error variance is the same as in repeated measures ANOVA, but you do it separately within your between groups levels. But otherwise it's exactly the same. In this example, we have 8 individuals. They have 2 different types of migraine. Dunk and eel. Let's call it throbbing and burning. I tried to find something yesterday. Throbbing and burning migraine. And then we measure each individual on 3 different occasions. Baseline after 1 week of treatment, after 2 weeks of treatment. And then we have the level of migraine for each individual on each occasion here. Personal mean for the 2 different types of migraine, mean for the different weeks, and so on. The cell mean, the combination of time point and type of migraine, total mean, and so on. And then we can calculate this sum of squares. Whatever is due to, whatever can be explained by type of migraine, what week it is, differences between cells, and so on. But if we have a look at the SPSS output, I guess you recognize them by now. What? We have, let's assume sphericity here. This is what week it is. What kind of conclusion do we draw about the time point? If it's week 0, 1, or 2. What do we say about the effect of time? The effect of week? There is a difference in average level of migraine between at least 2 of the 3 time points. But this effect of time is usually sometimes you see is qualified or modified or moderated by what type of migraine you have. We have a significant week by type interaction. So this means there is a general change. Well, there is a difference between at least 2 of the weeks when it comes to average level of migraine. But this difference between the weeks looks different depending on what type of migraine you have, because we have a significant interaction here. How would we continue from this? We have a significant interaction. It could be analyzed in 2 different ways. We could look at the effect of type of migraine on the average level of migraine separately for the 3 time points. We could do that with a t-test, for instance. 3 separate independent samples t-tests. Or we could go the other way. We could have a look at the change in level of migraine over time between the 3 different weeks separately for the 2 different types of migraine. Of course, it's not always clear what you want to do, but I think the last option sounds more rational. So this is throbbing migraine, and this is burning migraine. what does the result tell us? What do we say about throbbing migraine? We see here we have a difference in means for throbbing migraine. What is the probability of getting these huge differences between the 3 weeks if there is no difference between the weeks in the population that the sample is representing? How large is that probability? 42%. So what do we say? What conclusion do we draw about throbbing migraine? What do we do with the null hypothesis? We can't reject it. This treatment, there is no indication that it has an effect on patients with throbbing migraine. However, for patients with burning migraine, it seems to have an effect. There is a significant effect. There is a difference between at least 2 of the time points. And if we plot the data up, it looks like this. We can do all the pairwise comparisons here also. For instance, with a contrast, we could look, is that change significant? Is that change significant? So now we got results that we could report. It looks like this. 2 between, 1 within. We add 1 more between subject factors. So we have what type of migraine do you have? So we have what type of, and in this you don't get the between subject effects. You get that in a separate table, but I didn't include them here. This is for the effect of the within subject factor. In this time, in this example, what week it's the measurement is done, and how it interacts with the between subject factors. So in this example, we have what week it is, what type of migraine you have, but we also add age group, what age group you belong to. So what conclusion do we draw from this? There is an effect a week. So the average level of migraine differs between at least 2 of the weeks. We no longer have a 2-way interaction here with type of migraine. I might have changed the data. I can't remember. We have an interaction. We have an age group by week interaction that is significant if we assume sphericity here. What does that mean? Well, it means that the change over time, over those 3 weeks, in level of migraine, that change looks different depending on what age category you belong to. So we have a time by age group 2-way interaction. But that 2-way interaction depends on type of migraine, because we have a significant 3-way interaction. How would we continue from this? Well, we could split the file. You could do it in various ways, but I choose to do it like this. So if you have, and with the effect of time separately, in this case separately for the 4 cells, for the combination of type of migraine and age category. So we see that if you have throbbing headache, the treatment has no effect if you're a young patient, while the migraine decreases if you're an older patient. And the opposite, more or less, for a burning headache. So this treatment has a decreasing effect on the level of migraine for older patients with throbbing migraine and younger patients with burning migraine. Not for the 2 other groups. And that's also confirmed by the p-values here. We have a significant effect a week here and there, but not there and there. So that's a science paper, of course. Oh, we might be satisfied with Lancet also. Any questions? What do we have ANOVA for? What do we have it for? What do we test with ANOVA? We test one-way ANOVA, for instance. What do we test with the one-way ANOVA? One-way ANOVA, we have a continuous dependent variable, so we can calculate the mean. What do we test about the mean with the one-way ANOVA? We test the equality of the mean between different groups. Yes, you can call it levels of independent variable. So we have various groups, 2 or more groups, and we want to test, do the populations they represent, can they be assumed to have the same mean on this outcome variable, if I call it that. We test that. Two-way ANOVA, what is added? What is added to a two-way ANOVA? Another independent variable. So individuals have different combinations of the two independent variables. So they can be treatment A and B, and men and women, for instance. What kind of effects do we get there in a two-way ANOVA? What effects do we get? We do the analysis, we put in our data, we do the two-way ANOVA, SPSS presents results. What effects do we get there? We get 2 main effects, one for each independent variable and one interaction. What is that kind of interaction called? When you have 2, it's the interaction of 2 independent variables. Two-way interaction. If the two-way interaction is significant, what do? We split the file, look at the simple effect of one of the independent variables separately for the levels of the other independent variable. Yes. Three-way ANOVA. How many effects do we get here? What kind of effects do we get here? We have treatment, sex, and age. 3 main effects: treatment, age, and sex. What more do we get? 3 two-way interactions: treatment, age, treatment, sex, age, and sex. And 1 three-way interaction: age, sex, and treatment. Okay. ANOVA for dependent measures. Bad name. What should we call it instead? Make it clearer. Repeated measures. It's not good with repeated measures, right? It's much better to only have one value per individual, right? Right? No? Why not? It's only confusing. Does this person have a 2 or a 7? Well, what is it? It's only confusing to have several values. Or? More high power. Why? Yeah, especially one confounder. What confounder?
Individual variation.
Yeah, exactly. Good name. Inter-individual variation. Because, of course, whatever variable you have, some individuals will tend to have higher values and others lower, independently of the condition. If you only have one value per individual, you can't know if the value is due to that this person tends to be high or low, or if it's the effect of condition. If you have several values per individuals, you can calculate how much of the variation is due to inter-individual variation and separate that from the error variance, and you get higher power in the analysis. Mixed ANOVA. Do you think mixed ANOVA? What is mixed ANOVA?
Repeated measurement and like two-way.
Yeah, repeated and between subject factors. Is it popular with mixed ANOVA in our business? Do you think so? Yes? Why? What do we, quite a lot of us, not me so much, but a lot on Karolinska, what kind of research do you do? Clinical trials. What do you do in a clinical trial? You compare different treatments at different time points. What do you want to get when you do a treatment study and conduct a mixed ANOVA? What do you want to see in your results? Interaction. Why? Yeah, yes. Why do you want the interaction? Why isn't enough with the main effector group? Why? But you get effector group. There is, if you get the result like this, no interaction, no significant interaction, but a significant effect of treatment. So your treated group has a better value than the control group, but no interaction. Don't we get happy by a result like that? It indicates that it's better to get treatment compared with no treatment. No, we don't get so happy. Why? Because if there is no interaction, it indicates the difference between the groups have been there all the way, even at the baseline. So the difference between the groups is the same in the baseline of the treatment and follow-up. And we're not happy about results like that. It indicates there was a difference from the beginning. It doesn't have to be due to our treatment there is a difference. So we want no difference at baseline, difference of the treatment, and hopefully also still improvement, the difference at follow-up. So we want an interaction. There was no difference before treatment, but then there became a difference. Conclusion, the treatment has effect. How about the effect of time? But you want an interaction. You want that. When you do a controlled clinical trial. No difference from the beginning, but then you have it. Means that you have an interaction. Okay. So